Okay, what is impedance? Type of resistance, isn't it? Okay, so this links into everything that we did last week. How many of you can remember what we were talking about last week?
Transformer windings.
Transformer windings, yeah. Okay, the fact that we have capacitors as well, it all creates another form of resistance, doesn't it? Okay. Now, these resistances are more like volumes. Don't forget to take a sheet and sign in. Okay. These are volumes. These aren't just true values that can just be added together like we do little bits of resistance, because they're causes and effects. Okay. So we have to bring it to the realms of Pythagoras' theorem. Okay. Who can remember how to do Pythagoras' theorem?
3, 4, 5.
3, 4, 5 is one method. A squared plus b squared equals c squared. So we're going to be going through this tonight. So don't get scared when we start looking at that first slide. This thing works. Of inductance, capacitance, and combined circuits. Okay. So for us, we see the letter Z before. Okay. So this is where we start linking it to Pythagoras' theorem. Okay. Z is our impedance. It's the long side of the triangle. Okay. We have our resistance. The resistance is when you're looking at that piece of wire. Okay. Because that just has a standard form of resistance, doesn't it? The reactance side of it is this side, where we end up with either capacitance or inductance, or if we've got both. Okay. The reason this has been written down twice by me is because of the fact that it's always got to stay as a positive number. You can't change it into a negative, it must stay positive. So whichever value, either the resistance of the capacitor or the inductor, needs to go first and be taken away. It doesn't matter which way round you do it, as long as you're left with a positive number. Does that make sense? Fantastic.
Why does it have to be a positive number?
Because resistance doesn't go into the negative realm. Okay. Well, at least not for us. If you go into engineering, you will find materials that can go into the negative realm of resistance. But
Yeah.
that's beyond my knowledge.
Yeah.
For us, we keep it positive realm for simplicity. Okay. So this is just the formulas laid out for you. So you've got a copy of these formulas written down for you. Okay. Are you all happy with this so far? Okay. Don't panic too much if you've forgotten how to do it with the calculator, because we're going to be doing an example and we'll do it together. Okay. Of course, we've got a current formula. Okay. That's just Ohm's law, isn't it? Okay. The reality of this is when we look at this, you've got your normal voltage. Okay. You divide it by resistance or equal current. Where are we likely to use this? Let's try and use it in the real world a bit. Where are you likely to use that in the real world?
If you want to calculate the impedance of the circuit.
Yeah, you could backtrack. If you know the maximum current available, you can calculate the resistance.
In design?
In design, you will use it. Okay. So if I did my UO, so my nominal voltage to earth, and divide that by my ZE, what will that give me? I don't know if Paul's taught you that one yet.
No.
Is it PFC?
It is close to that.
PEFC.
What you're talking about is P something. Perspective fault current. There's two types of perspective fault currents, isn't there? Okay. We've got for this we'd be calculating our P perspective earth fault current. So in the realm of when we do our ZE, we'll be working out how much current is available at the main incomer for the property. Okay. You could always do it with you can do a test between live and neutral and work out your Z there, and then you could also work out from that your perspective short circuit current. Okay, there are two fault currents. Okay, so has he done ZE testing with you before? Or talked about it yet? last night talked about earth fault current testing, didn't you? Okay, so when you test out that Z value, you can actually work out how much current you'd have available for the event of a fault. Okay, what's the benefit of knowing how much current is available for a fault?
Because then you'll know what trips the breaker.
That's it, you can actually work out your trip current times. Okay, you can go to the disconnection graphs in the back and you can actually accurately plot it. If you can use those graphs very well, they're absolute dog shit. Okay? But it allows you to see how much current is there. So if you've got things like a 6 amp breaker, okay, a 6 amp B type breaker requires 3 to 5 times its rating to trip. So you know that if you've got more than that in your fault current, you know that you're always going to be able to trip that protected device, aren't you? Okay, because in the event of a live to earth fault, the circuit will have such a high shoot in the current demand that it will disconnect in a suitable time. Okay, does that make sense? Fantastic. So, we'll have a look at this first one then, okay? See how much, if anyone can remember the formulas from last week? Okay. So we have a circuit with 230 volts, 50 hertz supply, and a constant consists of a resistor of 25 ohms and an inductor of 0.05 Henry. Okay. Who can remember the formula we used to convert the Henrys into my XL? Anyone done any revision from last week? Anyone got their formula sheet on them so they could quickly look it up? See if they can remember it. Speak up, I heard the 2 pies. All remember that? 2 times pi times frequency times by the inductance measured in Henrys equals my XL. Okay? Anyone half remember it from last week?
It's coming back to me.
Okay, so I can put into this my values now, can't I? So we know 2 times by pi is a constant. What's my frequency in this question?
50
hertz.
50 hertz. And what's my inductance?
0.05.
Okay, so if you run that through a calculator, can someone do that for me?
You've got your resistor in there as well.
What?
You've got your resistor
That
in there.
comes next.
15.71 ohms.
They're looking at the answer. Someone cheated and just looked at the answers for me. Okay, 15.17 ohms. If you guys are doing the calculators, have a go at it. Make sure you're happy with how to do it.
15.71.
Sorry. Just checking you're awake. Two times pi times by the frequency of 50 hertz. Everyone able to calculate it? Anyone need me to run through it with the calculator on the board?
Yeah, please, yeah.
Okay, so on your calculator, do you want to pay attention for a sec? Can I help you? I've got a massive one here that you can look at.
Sorry, mate.
Okay. So the first thing you're going to do is you're going to hit the 2, and then you're going to times it by pi. To get the pi function, it's mainly down the bottom here, and you have to press the shift, and then hit that button down the bottom. Okay, you should get a funny little symbol here. Okay, Once you've done that, you can do times the 50 for the frequency, and then it's times 0.5. Press equals. If you end up with a funny symbol, you have this SD button to convert it to a standard number. So I get 15.707, which when rounded up, 0.71. Okay? Are you all happy with that? Okay.
So if you wrote it down as like 15.707, would that still be right?
So the correct answer is okay, so that doesn't answer the impedance, does it? That's just looking at that inductor. Okay, so now to work out the impedance, we have to add into this our resistance onto this. Okay, our resistance will go down to the bottom of the triangle. Okay, and it is 25 ohms. Okay, so we now use Pythagoras' theorem. Okay, if I was to do this side squared plus that side squared, it'll equal z squared. What's the opposite of a squared number? A square root. So if I square root the whole formula, it'll give me the whole number at the end, won't it? Okay, so that's why we make sure we square root the whole formula. You might have to be careful. Some calculators, you need to make sure that you put it in a bracket so it does the whole formula and not just the first number. Okay? Right. Who's happy to start putting that through their calculator? Who wants me to show them how to do it on the board?
Yes, please. No.
So you've got up towards the top, funny little looking tin box.
Yeah.
It's your square root button. Okay? So if you hit that, just to be on the safe side, we're going to put an open bracket in, just to make sure we're going to have no issues with this. It's going to do the whole formula. Okay? Next thing I'm going to do is I'm going to put my 25 in, just as normal. Okay? You should have an x2 number.
Yeah.
Okay, so you hit that after the 25, then put plus. Okay, you all with me so far?
Yeah.
Then 15.71, and then you're going to hit that x squared button again.
1571 mean, isn't it?
15.71.
Oh, sorry, yeah, sorry. I'll take that back. Sorry, mate.
Okay, and just make sure you don't end up with it saying error. Just put a closed bracket in. Have you all managed to get to this point?
No, not yet.
Yeah.
29.
And then you just hit.
Yeah, that squared button again. That x2. Okay, that squares it. Okay.
What's the likelihood of there being a question like this in the exam?
100%.
Right.
Inductance, capacitance, and reactance. 100% you will get a question on this in the exam. Okay.
Marks of the exam, is it?
9 marks.
Oh, that's alright. No marks.
This will be at least 3 marks for this.
That's fine. Good.
Is it round up?
5-2.
I've rounded mine up to 5-3.
Yeah.
Okay. The 6 rounds up the 2 to a 3.
What's this got to do with bloody turning on like a switch, man? Put the blood pressure on off. This is about.
It's so you have a deeper understanding of your testing.
I get you now. Now I understand you. That's all. I wasn't messing.
I know. The reality is, it's because that shows you where Z comes from. So the idea of you doing your tech certs at level 3 is so it's not just a case of you can whack in a circuit, because you do that from level 2. The idea now is that you're turning yourself into more engineers. And then an engineer will understand what he's testing, why, and what reading he will receive. Okay? So for us, we receive Z when we do our ZS testing. Why is it Z? Why is it not just resistance? Why is it not? Why do we have to refer to it as Z? It's because it goes through that coil in the transformer. It's not a true resistance in there. So it has a different effect to a standard piece of wire running through a circuit. Okay, does that make sense? Fantastic. Okay?
So there's a question like this in the test.
Yes. Okay. So now I've got A done. So I know that my impedance now is 29.53. How am I going to work out my current flowing in the circuit? How will I work that out?
Current equals voltage divided by
Keep going.
voltage.
Voltage divided by voltage.
No, sorry, voltage divided by resistance.
Yeah, which resistance? So we know that Ohm's law, it's voltage divided by resistance equals current. Which, all three of these on this triangle are resistances. Which one are we aiming for to work out the current in this circuit? Z. Okay? So to work out this next one, I'm going to do voltage divided by Z equals current. Okay? It's just Ohm's law, isn't it? We've just got to make sure that when we do this, that we are using the right resistance value in the formula. Okay? Does that make sense? Okay. So we're going to do, what is the voltage that we've got?
230.
230 volts. What's my Z then? 29.5 or 29.53? Okay, so if you divide that, what do we get? 230 divided by 29.5 or 53.
7.78. So it could go 7.8.
So 7.78 amps. So we now know that's how much current will be needed in this circuit. Okay?
To make it trip.
To make it work.
Did you say that the breaker needs 3 times its nominal rating to?
If we're going to go down the route of trip rating, yes. So if you were doing this as a ZS test, okay, that would be telling you that your fault current would be 7.78 amps. So it'd be like a TT system, but the amperage is really low.
And the breaker would flick.
The breaker wouldn't flip it down, amperage, would it?
Maybe that's go up to like 5 times its.
3 times its rating minimum, so 18 amps for a 6 amp breaker for it to even think of tripping. This will just get warm eventually. It might take 5 days to trip with a 7 amp fault current.
Would this be working out the amp rating of the main on and off switch?
So this, what we've done here is more looking at what amperage the circuit needs to operate.
And
Okay.
we're talking about a lighting circuit or a ring main, yeah?
So if you're more like a motor, because that coil wire.
Okay.
So we've got a motor, which is our inductive load,
Yep.
which is 0.05 Henrys. So we need to know how much current is needed to get this motor to actually work in this circuit.
Okay.
Okay, does that make sense?
Yep.
That's it. So we worked out how much current is needed to get this motor to work.
Yep.
From that, you can go, I need a 10 amp breaker now.
Yep.
From there, you can go, so my cable size, I'm mostly going to go for a 2.5mm cable because of it being 10 amps. I could put in a 1.5mm, but I know if I put 2.5, I'm going to future-proof it and allow for a start-up current as well. Okay, does that make sense?
Yep.
So it can apply to designing and everything. Okay?
Yep.
Perfect. Okay. Right, so we're now going to have a go with it with a capacitor now, okay? So we've done it with an inductor. So if we now look at it with a capacitor, what changes is the first formula for working out this side. What's the formula for working out the XC of the capacitor? You've got a formula sheet, use it. Been given to you for a reason to get used to using it to help
So
you.
it's 2 times pi times voltage times the frequency
out of 1 there.
Yeah, 1 divided by.
1 divided by.
Yeah, sorry.
There was always 1 divided by.
So it's 2 times pi.
The reality is, this is what we went over last week.
Yeah.
You all need to be looking at your notes between now and next week, because this one subject is worth 9 marks in your exam. You will 100% get a question on this in the exam, and in the last 5 exam papers I've looked at, it's always been worth 9 marks. How many marks do you need to pass this exam? 30. So this one subject is something that you should all be taking a key interest in and looking at. Okay? If you can get your heads around this from start to finish, when it comes to the exam, you'll be laughing, won't you? Because you get 9 marks from this. How many marks are in the design question?
15.
15. That's 24 marks. And how many marks do you need to pass? 30. So you only need to get 6 more marks to pass that exam. And that's just going off 4 questions.
I think the first page is common sense questions.
First page is quite often common sense.
Is that like knowing your name, address, date of birth? That's 3
Pretty
marks.
much if you can write your name.
Bank details, last 3 digits on the back.
So, you all need to realise that this is really important to be looking at your notes. This is why I give you the handouts, so you have lots to take away. Okay? So if I've got my 1 over 2 pi, what's my frequency in this example?
100 hertz.
Okay? What is my capacitance?
10.
10 what?
10 UF.
Microfarads.
Microfarads. Don't forget, whenever we deal with capacitors, okay, we have a funny shaped U here. Okay? It means micro. It's an engineering prefix, isn't it? What is it to the power of?
Minus
6.
-6. Oh.
10 into 10 minus 6.
Okay? It's very important we include that in the formula. If you don't include it in the formula, you will come out with the wrong answer and it affects everything else. Okay? Right. For those of you that are confident in putting this into your calculator, please make a start. I will go through it again. Okay? So, some calculators, for those of you that aren't very confident with calculators at the moment, they have this function button here. This function button allows you to put this in as an actual fraction. So you don't have to remember to put brackets in and things like that. If you don't have that function on your calculator,